Warm greetings and welcome to dear students. Today we are going to deal about the course on solid mechanics in the topic of the bending moment and the deflection of beams. So bending moment is nothing but the product of the force into perpendicular distance, and the unit of bending moment is kilonewton meter or Newton meter, or you can say in the case of Newton into millimeter. So whenever the load is applied on a given beam, what are the types of beams are available? Definitely there will be a deformation is going to happen in the beams. So that is called as a deflection of beams. In addition to that, there will be a rotation of the beams due to the applied external moment. The moment may be of the point load, uniformly distributed load, uniformly varying load, and a couple or the bending moment. And what are the types of methods are there to find the deflection of beams? The types of methods available are the number one, double integration method. The second method is Mechanics method. Third type is the moment area method or Morse theorem method. And fourth method is column analysis method. In addition to that, we can go for the Steiner-G method and other empirical methods are available. But in the case of the third semester solid mechanics, we are going to deal about the first four types, that is double integration method, Mechanics method, then moment area method or Morse circle method, or in the case of the column analysis method. And moment area method is also available in the case of the third semester solid mechanics. The first method, which is called as the double integration method, it is a very simple method and that will be available for the simple beams like simply supported beam, cantilever beam, and the overhanging beam, so either single or double overhanging beams. But here the limitation of the load on the beam is a pure simple load. So complicated load or discontinuous loads in addition to the vertical load or the UVL, UDL, that cannot be solved in the case of the double integration method. So in the case of double integration method, the main equation used to solve the deflection and the slope on a given beam due to the external loading is EI d square y by dx squared is equal to the bending moment. So EI d square by dx square, that is the left hand side, that is equal to the summation of all the moments in the case of where the moment is applied in the case of a beam. So M is the moment where the section is going to have the deflection required or the slope is required. If you take a simple supported beam or simply supported beam, if you are applying a central point load on the beam which is of span L and the supported hinge and the roller support on the two ends, the total deflection occurred can be determined by using the double integration method. The total deflection occurred delta or delta maximum or Y maximum, that is equal to WL by 4080 EI. So W is the apply load, that is central point load, and L is the span of the beam. EI is the rigidity of the beam material. The product EI we have to find, that is called as the fluxural rigidity of the given beam. So based on the material given and the cross section, the value is going to vary. So from that you can find the moment at the either central point or where L by 4 or 3 by 4 you can find it. So if you are finding this equation, EI d square y by dx square is equal to the M value. So M here is equal to W by 2 into X. If you are going to integrate twice, you will get that final value of delta. You will get the two constants C1 and C2 that can be applied from the given two equation. After that, you can find the slope and deflection on a given beam. So in the case of simply supported beam, at the central only you will get the maximum deflection, that is equal to W into LQ by 48 EI. So only the Young's modulus value is same or the cross section of the beam is same. Throughout the beam you can apply this method. Otherwise you cannot apply this method, right? Whether the cross section or the Young's modulus is varying continuously from section to section on a given beam. So the deflection of the beam can be measured in terms of the meter or millimeter by using the dial gauge in the case of the structural technology center, that is possible. Or in the case of UTM also you can do this type of experiment. So that is the given value. So the I is varying based on the cross section. For example, if it is a circular beam, it is pi d per 4 by 64. So if it is a rectangular beam, the moment of inertia I is equal to b d cube by 12. If it is a square cross section, which is of side A, I is equal to a into a cube by 12, that is a per 4 by 12. So you can able to determine wherever the deflection and the rotation, that is called as the slope, is required, you can find it. So at the midpoint of the simply supported beam, the maximum deflection occurs. So where the maximum deflection is occurred, the slope will be always equal to 0. So you can able to find the constant, one constant C1 and C2 based on the known conditions. Because simply supported beam at the central point, the deflection is maximum, the slope will be equal to 0. But at the support end, definitely there will be a slope, that is theta A and theta B. So A and B are the points, that is at the support ends. Can be determined using these, right, slope equation. Ei dy by dx is equal to integral of m. So that value you can easily predict it. So based on that, you can solve the problem in the case of double integration method. The main limitation is if it is a simple loading on the beam and also a determinate beam, and also the EA value is constant throughout the beam or the span of the beam, we can be able to adopt this method. So in the next class, we can see the other type, that is the Mechanics method and the moment area method or Moore circle method and conjugate beam method. Thank you very much for patiently listening. Thank you.